Here begins a lesson on acids and bases and how they relate to equilibrium. Again, it's another opportunity to practice our equilibrium expressions, but this time dealing with acids and bases. Our unit will start off with a review of the definitions of what an acid and a base is. In this particular part of the lesson, we'll talk about the Arrhenius definition of acids and bases. We'll remind ourselves about the Bronsted Lowry. So acid-base theory is our first of our lessons. Secondly, we'll talk about the pH scale and the autoionization of water. How do we go about calculating pH and then its partner, of course, pOH, for the concentrations of bases? So calculation review of our first year of chemistry. We talked about strong acids and strong bases versus weak acids and weak bases. We talked about this in our initial lesson on electrolytes way back when. And strong acids and bases, as any strong electrolyte, will be 100% disassociated, where weak acids and weak bases, like other weak electrolytes, set up our equilibrium that partially ionize. And then when we have strong versus weak, and we can see that in the equilibrium. When we partially ionize, we move the equilibrium expressions known as Ka for acids and Kb for bases. For those weak acids and bases, this set up equilibrium. That math will be a whole lot similar to the math back in the last chapter when we learned about concentration equilibriums, so Kcs and Kps. So we're introducing equilibrium expressions for Kas for our acids, Kbs for our bases, and then we extend the conversation to salts. We consider the acid-base properties of salts, and we call this property hydrolysis. Where the conjugate base or the conjugate acid of a strong acid or base undergo a process of hydrolysis, which just really means adding water to the solution. And then finally, we're going to introduce a brand new theory of acids and bases, the Lewis theory. We talked about Lewis dot structures in an earlier chapter with the Vesper theory in the molecular shape of molecules. When we drew dot theories, we called those Lewis dot structures. Well, this is indeed the same gentleman. He also worked in acids and bases, and we'll talk about his concept of how he defined acids and bases. A good majority of our lesson starts off with review of our first year chemistry and how we defined acids and bases, how we calculated the pH and introduced the concepts of strong versus weak. Indeed, those will all be review topics. The new lesson is an application of equilibrium. How do we carry last chapter's equilibrium constants and ice charts into Ka and Kb hydrolysis problems? So let's go ahead and get started with the first page of our brand new note pack, reminding ourselves about the very first definition we first learned about what acids and bases are. So the very first definition of what we learned about acids and bases are known as the Arrhenius definition. Again, this is a man's name, Arrhenius. It's the last name of a chemist who defined acids and bases. Acids are those substances that, when placed in water, release hydrogen ions. We said that any substance who begins with an H An ionizable hydrogen would be defined as an acid. And when placed in water, bases will produce a hydroxide ion. So we can symbolize that and we can say, well, a metal would have the hydroxide attached to it. So hydroxide, again, is a polyatomic ion. And if it starts with an H, it's an acid. If it ends with an OH, it's a base. These are probably our most familiar definitions of acids and bases. We understand that acids and bases, to release their ions, must occur in an aqueous solution. So it is shown as AQ. We talked a great deal last year or in first year chemistry that although this is a very good definition for the vast majority of acids and bases, there are some instances where the Arrhenius definition just doesn't work. And we introduce an idea of ammonia. Ammonia is a base. Ammonia turns litmus paper blue and has a pH greater than 7. It feels slippery. It does everything that a base is supposed to do, and yet it doesn't end with an OH. So there are a few substances that really are acids and bases that just don't start with an H or end with an OH. So that was the reasoning that we expanded the definition to the Bronsted-Lowry theory. So here we have Bronsted-Lowry theory. Bronsted-Lowry are two different chemists. There's a hyphenated name, Bronsted and Lowry, working together on definitions of acids and bases, came up with the following. Acids we call proton donors. Proton is another way of saying a hydrogen ion. Proton and hydrogen ion are used interchangeably. A base is a proton acceptor. We talked about conjugate pairs. Acids and bases always come in pairs known as conjugates. Where they only differ by one hydrogen ion in their formula. According to Arrhenius, HCl is an acid. It starts with an H. It's going to release a hydrogen ion when placed in water. But it also obeys this definition. According to Bronsted-Lowry, when it dissolves in water, it does indeed release its hydrogen ion, but the water accepts it. Here we have a proton donor, HCl. And if this is my proton donor, then water is my proton acceptor. HCl is labeled as an acid, and here our water is labeled a base. It acts as a base. On the other side, we see that the conjugates have formed. The conjugate of the acid only differs by a hydrogen ion. So if HCl is an acid, it produces its conjugate base. And see, HCl, Cl. See that there is a difference of it has an acid that has lost its hydrogen, so its conjugate base is chlorine. See, conjugate base. If water was acting as a base, it produces its conjugate acid. And notice that it has an extra proton. So here is its conjugate acid. So it's called a protonated water, also known as hydronium polyatomic ion. Hydronium is indeed the acid ion that's produced in this solution. The more hydronium in solution, the more it affects the pH of that solution. The direct measure of the concentration of hydronium is known as the pH. Remember that finding the pH, we can take the negative log of that hydronium ion. And this hydronium ion, again, remember H3O plus, polyatomic ion, reminds us that we indeed have an acid. And this is that Bronsted Lowry theory. And again, this H3O plus is protonated water. So just continuing practicing, looking at conjugate pairs, we have this general equation, HA, again, so we have our acid, and we know that because it's starting with H, and then we have our water, and in this case, water is acting as our base because our acid is clearly labeled here. So then over on our right side, we have our conjugate acid. We can see that because it has the base has become the proton acceptor, so therefore it now has 3 hydrogens, so therefore conjugate acid. And then over here we have our A negative, which is our conjugate base. Notice that going from HA to A, it has lost the hydrogen. So we have our acid plus our base to form our conjugate acid and our conjugate base. So this is an equilibrium. There is a competition for this H plus between the water, so our base, and our A negative, our conjugate base. And the stronger base controls which direction this is proceeding in. If water is a stronger base, this water, it takes the H plus and the equilibrium moves to the right. Okay, so the stronger, so in this case, H2O is stronger than A minus. These two bases, the base and the conjugate base, are competing for that H plus. So we will have a chart here to look at in just a minute where we can compare the strength of bases. But again, the stronger base, and it will push away or push in the direction. So if the stronger base was on the left, it will push to the right. If the stronger base was on the right, it will push the equilibrium to the left. Let's keep practicing by labeling our conjugate pairs. I'm just going to write this so that it's in a straight line and easier to see. If we have NH3 and water, to give us ammonium, so we have ammonia and water to give us ammonium and hydroxide. So first thing we're going to do is to find on the left side and the right side pairs that only differ by 1 hydrogen. And H2O and OH, again, only differ by 1 hydrogen. So the conjugate pairs only differ by 1 hydrogen. Notice we go from NH3 to NH4. So this is a conjugate pair. 2 H's and 1 O versus 1 H, 1 O. Only differ by 1 hydrogen. These are conjugate pairs. And then next, to figure out which one is the acid and which one's the conjugate base, or which one's the base and the conjugate acid, the one that has more hydrogens is always the acid. So let's look at this one. I have 3 hydrogens, I have 4 hydrogens. So this must be my acid. So therefore, this is the base. And if this is the base, my water must be acting as an acid. So on the left, I have my acid and my base. So on the right, I'm going to have my conjugate acid. And again, on the right, this must be my conjugate base, but let's just compare. Notice I have 2 H's and I have 1 H. So this is more H's. This has got to be my acid. So therefore, this is my conjugate base. There will always be 1 acid and 1 base on the left side, and 1 conjugate acid and 1 conjugate base on the right side. So water in the last example acted as a Bronsted Lowry acid. And if we were to flip back and look at our last slide, we saw here that water acted as an acid. It was the proton donor, right? And then a couple slides ago, we saw that water acted as a base. It was the proton acceptor. So when water can act as a proton donor or a proton acceptor, it is called amphoteric. Again, it can act as a proton donor or a proton acceptor. And here's just another picture of showing if I have water, I can have water acting as an acid or a base. Again, depending on if it's going to accept the proton or if it's going to donate the proton, make H3O or OH minus. Let's try some of this. Let's try to find the conjugate bases of each of the following acids. So if I have HClO4, which is perchloric acid, its conjugate base would be losing a hydrogen. So we're going to lose, that only has 1 hydrogen to lose, so we would have we would have ClO4 with a -1 charge, which is perchlorate. So here I have perchloric acid becomes perchlorate. And again, remember, we're losing the hydrogen. And so by the loss of a hydrogen, it makes the charge decrease by 1. If you think on the number line, HClO4, perchloric acid, had a neutral charge, 0. And if it's going to decrease by 1, it's going to go down to -1. Let's look at our next one, H2S. This is hydrosulfuric acid. To lose an H, there's 2 H's here, so I'm going to lose 1 H. It will just become HS, which is hydrogen sulfide ion. And again, I went from neutral. Now this is a -1 charge. You just say negative or -1. Let's get pH4 plus 1. All right, so if I'm going to lose the hydrogen, I then go to pH3. And again, if I think on the number line, I'm going to lose, I'm going to go from 1 to 0, right? So I just have no charge here. And let's look at HCO3, -1. And if I lose an H, I'm just going to have CO3, and I go from -1 to a -2, right? I'm just losing 1. So I'm going to a carbonate ion. Let's look at some examples where we have to find the conjugate acid of each of the following bases. So here's my bases. Let's find the conjugate acid. So I just have Cn minus. So a conjugate acid is going to have that extra H. So it's going to grab an H. So then we go from Cn minus to HCN. And then when we look at charges, if we add an H plus, the species increases by +1. So if we think on the number line here, if I was a -1, I'm going to go up to 0. So I now have HCN, or cyanic acid. What about SO4 minus 2? If I add an H, I will have HSO4. And again, I would be going from -2 to -1. Water acting as a base, H2O. Grabbing an extra H will make it H3O. And I went from neutral to, if I increase by 1, I'm going to +1. And again, this is our hydronium ion, or protonated water. And then last, we have HCO3, -1. So I'm going to add an extra H, so that'll give me 2 H's, H2CO3. And this takes me from a -1 to a neutral. What's interesting about HCO3 is that this is called amphoteric, because notice that it can act as a base here. It can form a conjugate acid by accepting a hydrogen, but here it can also lose a hydrogen. So this could be the conjugate base of, the conjugate acid of CO3 with a -2 charge, right? It could accept a hydrogen to go from CO3 minus 2 to HCO3 minus 1. And then here it can act as a base and form a conjugate acid. So that is called amphoteric. So let's look more into this one. That hydrogen sulfite ion that we just looked at is amphoteric. So let's write a reaction for this ion with water. So we've got HSO3 minus, so we have our hydrogen sulfite ion plus water. And if this is, let's see, this ion acts as an acid. So if this is our acid, then water is acting as our base. So then if our acid is it's going to be a proton donor. So we're going to lose that. We're just going to have SO3 with no H. Remember, we're going to go down on the number line. So we go from a -1 to a -2. So this would be my conjugate base, right? These two only differ by a hydrogen. And then since my base is a proton acceptor, it's going to go from H2O to H3O plus. Again, the proton acceptor goes from neutral, we go up on the number line. So it gained, it's now +1. So this would be my conjugate acid. H3O is also hydronium, right? So here again, in this case, they wanted us to write an equation for the reaction of hydrogen sulfite as an acid reacting with water. So water must be our base. Our hydrogen sulfite would be our hydrogen, or our proton donor. So its conjugate base would be without that hydrogen. And therefore we would be losing. We're going from -1 to -2. My base would be proton accepting. So its conjugate acid over here would be H3O+. Let's look at that same ion, hydrogen sulfite, HSO3-. Reaction of this ion with water, in which this ion acts as a base. So we're going to have it acting as a base. So therefore, our water must be acting as an acid. So therefore, to form a conjugate acid, this base has to gain a hydrogen, right? So we go from 1 hydrogen to 2 hydrogens, H2SO3, and we go from a negative to a neutral. So conjugate acid, again, the difference between these two, this one has 1 more hydrogen, therefore it's the acid, right? 2 hydrogens versus 1 hydrogen, and we said that we were starting with the base. So the conjugate acid has to have 1 more hydrogen. And then if we look at water, again, it's the acid, so it is donating an H. It's going to lose that H. So we're going to go from H2O with the acid, and its conjugate base is going to be 1 less than that. So we would be stuck with OH, and we went from a neutral to a -1. So here we went from -1 to neutral. Here we go neutral to negative, so we go in the opposite direction. And again, this is called being amphoteric, where a species can act as an acid or it can act as a base. Here's a tricky one. So lithium oxide is dissolved in water. And if we think back, lithium we know is an alkali metal, and oxygen is -2, so we're going to have Li2O. And we know when it's dissolved in water, it's going to separate into those ions. So we're going to have Li+, we'll have 2 Li pluses, and we'll have O -2 ions. And we know that these Li pluses are just going to be spectator ions. So we're just going to disregard the actual lithium part. So let's just take this oxide down here. When this oxide is dissolved, reacts with water. So in this case, we have our oxide, which is very basic, very, very basic. And so our water is going to act as an acid. So let's think about what's going to happen over here. We're going to have our conjugate acid. So our acid is going to accept a proton, so we're going to have OH-. Again, we're going from base to acid, and we can see we went from -2 to -1. Let's find what our conjugate base is. So we have our acid. It's going to lose one of those H's to form our conjugate base, and we're going to be OH-. Again, we know that this has more H's than this one, so it is our acid. Here's our conjugate base. This has more H's than our base, so it is our conjugate acid. And we can see here that our reaction that occurs, notice that we have a very, very, very basic hydroxide concentration. We know that the greater the hydroxide concentration, the greater the pH is. We know the greater the pH, the more basic a solution is. So the stronger an acid, the weaker its conjugate base. And if we were to just kind of show this and write an example out here, let's say we have just a generic HA. This is my acid. And let's say that it's strong. And let's just put it in water. And if it is strong, it's going to push really hard to the right. And it's, let's see, so this is my acid, so I'm going to have H3O plus and A minus. So this would be my conjugate base, right? The HA There's an H, so this would be my conjugate base. This would be weak. And if it's weak, it's only pushing back just a little bit. Same with my base. If I were to say B for my base and say that it's strong, again, strong is going to push really hard in the direction that it's away from it. Again, we'll have our conjugate acid here. This is my base. So my conjugate acid will be weak. So just push weakly back. But I could also reverse this, and I could say if I had a strong conjugate acid, so let's say that I had a weak base plus water. I'm going to have a very small arrow here because it's weak. And then if my product, if I had a strong conjugate acid, I'm going to push, it's going to be strong, pushing away from that conjugate acid. So if it's a weak base, it's only going to push a little bit away. If it's a strong base, it's going to push a lot away from it. Whatever the weak side is, it's just showing that it's going to push very little. If it's pushing strong to the right, we're going to have a big constant. If it's pushing strongly left, we're going to have a K constant of less than 1. So that would be reactant favored as opposed to product favored. Here's a chart that we'll be using for reference that just shows us these are conjugate acid-base pairs. So the stronger the acid, so really strong acid, HClO4, its conjugate base, again, notice that I'm with one less hydrogen to get my conjugate base, and it is very weak bases. So the stronger the base down here, I can see O2 negative as a very weak acid, OH negative, or conjugate acid. So we're just able to kind of compare even. And then we're able to see kind of right here in the middle, HF, we can say weak acid, it's going to give me this conjugate base, also pretty weak. But the stronger the acid, the weaker the conjugate base. Another thing to note is that strong acids completely transfer their protons to water. It leaves no undissociated molecules in solution. So there is not an equilibrium. Now there are 7 strong acids that you should be able to know and recognize. They are HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid. These are binary acids. We then have 3 acids that are monoprotic acid, HClO4, HClO3, and HNO3. And then 1 diprotic acid, H2SO4, sulfuric acid. So these 7 are really important to be able to know, recognize that they are going to completely 100% dissociate. So if I took HCl and put it in water, it is going to 100% dissociate in solution. So I'll have H3O plus Cl minus, and I can measure the pH. There's no need to do an ice chart with this. Okay, there's not going to be a the equilibrium, I can measure my pH concentration from my HCl, and it's going to be the same as my product here by taking the negative log of my H3O plus ion. So what about weak acids? Well, weak acids only partially dissociate in their aqueous solution. They exist in the solution as a mixture of acid molecules and their constituent ions, which, if you think about it, is the pure definition of equilibrium. And if we were to think about an example here, let's say we looked at acetic acid, HC2H3O2 in water. To set up this equilibrium with H3O plus and acetate. And with this, we can take and we can find our equilibrium constant for our acid. Remember our products over reactants, so the concentration of H3O plus and acetate minus over, so products over reactants. Remember, we don't include concentration of solids or liquids. It wouldn't make sense to just have, there isn't a concentration of just pure liquid water over my molecule of HC2H3O2. So we have our ions over our molecule, right? And our products over our reactants. So by doing this, we're showing that we have this equilibrium existing in the solution, showing the mixture of acid molecules, their constituent ions. Remember that conjugate bases of weak acids show a slight ability to remove protons from water, and the conjugate bases of weak acids are weak bases. If we were to just go back and look at that last bit, when we have weak acids and weak bases, this is where we're able to set up those equilibriums. We have strong acids, they're going to 100% dissociate. We don't have the equilibrium set up. Same with strong bases, they're going to 100% protonated in an aqueous solution. We don't have the equilibrium with the strong acids and the strong bases, but we do for this whole middle part. So just because a compound contains hydrogen, it doesn't mean that it will exhibit acidic behavior. For example, CH4, methane. If I were to look at methane's structure, we can see that that we have carbons surrounded by 4 hydrogens, and it is not an acid. In fact, it's actually a nonpolar and won't even dissolve in water because likes dissolve likes. But chemists have actually helped us to be able to identify what's an acid, just even by writing it. For example, acetic acid is HC2H3O2. And by writing this H right here out in front, it's showing us that this is the acid hydrogen. These ones that are buried, not acidic hydrogens. So with inorganic nomenclature, you will always see that acidic hydrogen written first. And obviously with CH4, it is not, methane is not an acid. So this is just emphasizing what we've been saying, that in every acid-base reaction, the position of the equilibrium favors transfer of the proton to the stronger base, or it favors the stronger acid. So again, if I have a strong acid, I'm going to have a weaker conjugate base. A strong acid on one side is going to push away from it. If I have a strong base on the left, it's going to push away from it, which means if I have a strong acid pushing left, I'm going to have a very weaker pushback. strong pushing this way, that means I'm going to have a weaker push back in the other direction. So equilibrium will contain more of that weaker acid and weaker base, less of the stronger acid, stronger base, again, because I'm pushing that equilibrium away from it. So it is going to produce more of that weaker base or weaker acid. Let's look at an example here. So for the following proton transfer reaction, we're going to use this table. We're going to look at HSO4 plus CO3. So first, actually, let's find our pairs. So we have our acid here, and then, of course, we've got our base. So let's find our conjugate, SO4. So we've got our conjugate base, HSO4 to SO4 minus 2. So if we have our base here, we must have our conjugate acid. So let's find both of our acids on our list. We got HSO4, which is right here. This is my one acid. Let's look at my other acid, HCO3, which is down here. And again, as we go up, they get stronger. So who is stronger, HSO4 or HCO3? And we can see here that our HSO4 is stronger. So we know that if we have a stronger acid, it's going to push away, and my equilibrium is going to be pushed to the right. And we can also double check this. So this was my acids that I looked up was HSO4 minus and HCO3 minus, and HSO4 was stronger. Let's look at bases just to double check. My two bases were CO3, 2 minus, and my other base, SO4, 2 minus. So let's look at my bases over here. Let's find CO3 right there and SO4 here. Remember, as we go down, they get stronger. So my stronger one here is going to be my CO3. So again, I'm going to look, and where is my CO3? My CO3 is on the left. And again, if it's stronger, it's pushing away from. So in this case, I'm going to have my equilibrium going to the right. So my Kc is going to be greater than 1. Let's look at another example here. If I've got HPO4 and H2PO4, these ones are going to be conjugates. And we know that this one has more hydrogens, so this is going to be my conjugate acid, meaning my HPO4 has got to be my base. And if I have H2O and OH, this has got to be my conjugate base. So my H2O here must be acting as an acid. So now let's look at these two. Let's look at my acid. If I have H2O and I've got H2PO4 right about here, and even though H2PO4, this is the similar setup here. So this, my H3PO4, H2PO4, we can see it's right about there, is going to be stronger acid. And let's compare my bases. OH versus HPO4. OH versus HPO4, again, right around here. My OH is stronger. So, stronger base. So when I have stronger acid, stronger base on the right side, that means it's going to push my equilibrium left. It's going to push it away. And so my K is going to be less than 1. Just like in this previous example, our Kc will be less than 1 if my equilibrium is getting pushed to the left. And let's do one more example here. This one has us looking at aqueous ammonia ion. So we've got NH4 plus reacts with aqueous hydroxide, forming an equilibrium with ammonia and liquid water. So NH3 and H2O. Okay, so let's find our pairs here. I've got NH4 and NH3. I've got more H's here, so this is my acid, and this is going to be my conjugate base. And here I've got my pairs. I have more H2O, more H's on the right, so this is my conjugate acid, and this must be my base. So let's compare my acids. NH4 versus H2O, acid, conjugate acid. So when I compare my two acids, NH4 plus and H2O, so my NH4 plus wins, stronger acid. Let's look at my bases though, to double check my bases. My two bases are OH and NH3. So here's my OH and NH3. And again, stronger is down here. So my OH is stronger. Stronger base. So I have stronger acid, stronger base on my left, which means it's going to push my equilibrium away from it. It's going to get pushed to the right, which gives my K a value of greater than 1. The greater arrow will be on the right with a gentle pushback to the left. So again, with that K greater than 1, we will favor the product. And in this lesson, we have reviewed the Bronsted-Lowry theory, the acid-base theory, and you are now ready to move on to the next part of lecture.